So welcome you back to today's lecture. So if any one of you have any doubts from previous lecture, you may ask them. If any doubt is bothering you. Okay, if there are no doubts, let me begin with the next topic. So what we have been doing so far was essentially considering only the data summarization or the data reduction, because that is one of the important components of any statistical inference problem. First, you try to structure your data. And that we did that if you introduce the notion of sufficiency, then it makes sense to restrict yourself to only those statistics which depend on observations only through the minimal sufficient statistic, or if complete sufficient statistic exists, then such a statistic would be minimal sufficient. Now, we were dealing with statistical inference problems. So I briefly stated what is a statistical inference problem is. So I have a random sample, x1, x2, xn. This is from some family of distributions f theta, theta belonging to capital theta. Functional form of f theta is known, but this parameter theta may be unknown. So what is unknown about the population is only this parameter theta, which is basically a part of a parametric statistical inference problem. And in this course, we are restricting our discussions only to parametric statistical inference problems. Now here, knowledge of theta yields the knowledge of the entire population. Right? So estimation of theta becomes important. Moreover, theta itself may represent some important characteristic of the population, such as population mean, variance, etc. And there may be a direct interest in obtaining an estimate of theta based on the sample, because that is the only information you are having about the population, which is in terms of a sample. Now, sometimes there may be an interest in obtaining a point estimate of some function of theta. So there may not be a direct interest in theta itself, but some function of theta for a given function of tau theta. So goal is that based on a random sample x1, x2, xn from the population, find a good estimator of tau theta. So a point estimator of tau theta is a function wx of the random sample. Right? So I want to use this sample x to get an estimate of tau theta. So that means my estimators would be a function of sample observations, so wx. Now note that an estimator wx is a random variable, whereas an estimate is an observed value of the estimator based on observed sample. So estimator is kind of a rule, right? You define estimator is kind of a rule, right? It tells you what you should do after the data has been observed. Now note that it is important that your rule is predetermined. It should not depend on the data. The rule should not depend on the data. Its value will depend on the data, but as such, the rule should not depend on the data. For example, sample mean. Sample mean is a rule which tells you if your data has been observed as x1, x2, xn, you calculate its mean. So that means sum of the observations divided by n. So it tells you a rule to determine an estimator. So it is important that estimator is determined well in advance before the data has been taken by appropriately choosing what estimator one should use. Because if you choose it after obtaining the data, then there is a possibility that your estimator is influenced by the data which you have observed. And then, as many people say, that you can prove anything through statistics. That would be true only when your rule is biased in the sense that it has been chosen after the data has been taken. And it is biased towards what data you observe. Right? So rule that way as an estimator or in general a decision rule has to be defined or chosen well in advance before data has been taken. An estimated WX, note that I have taken a general definition of a WX. Normally this tau theta will be taking values in a certain set. So you would like WX to be restricted to only the values of tau theta. For example, if you are estimating tau theta is suppose a probability that X is greater than 1. So it depends on the theta. So you would restrict your estimator to be taking value only between 0 to 1. But here I have considered a general definition of a estimator so that my estimator can take values outside that also, outside the range of tau theta. But as you see, we'll take care of that through other criteria. That means I would be choosing only those estimators which are close to tau theta. So if it is falling outside the range of tau theta, they would be with high probability anyway get discarded. So just for a general discussion, I do not want to restrict my WX to be taking values in the range of tau theta only. So the first thing which comes to anybody's mind is, what are the different methods of estimation one can think of? Now you have studied these two famous methods of estimation at your bachelor's level. One is the method of movements, which is due to Carl Pearson. The idea is very simple. Suppose your parameter is k-dimensional. Then what it says is equate first k sample movements to first k population movements and solve the system of simultaneous equations. Now, sometimes what may happen is you may require more than k equations. Will be required to get method of movements. An example could be, suppose x1, x2, xn are IID normal 0 theta. Then equating first sample movement is equal to population movement does not give you anything because it gives you x bar is equal to 0. So you take only those movements where involvement of theta is there. In this case, the first movement involvement of theta is not there. So I would just ignore this. So a modified definition could be equate first k sample movements to first k population movements that depend on theta and solve the resulting system of equations. That one can take as method of. So what is the method? So let us say mj is the jth sample movement, which is 1 upon n, summation I is equal to 1 to n, xi to power j. Mu j prime theta is suppose the first population, jth population moment, which is expected value of x1 to power j. So you can put a theta over here. So consider system of equations, mu j prime theta is equal to mj. The solution of above system of equations is the method of movement estimator of theta. There are certain issues. Sometimes this system of equation may not possess any solution. But mostly it would possess, and then whatever estimator I get by solving it is called the method of movement estimator of tau theta. So first I obtain the method of movement estimator of theta 1, theta 2, theta k. And the method of movement of estimator of tau theta is taken as tau theta tilde, where theta tilde is a method of movement estimator of theta 1 tilde, theta 2 tilde, and theta k tilde. The idea is very simple, very intuitive, that you equate sample movement with the population movements, because if your sample is large enough, your sample is a true representative of the population, then the sample movements would be good approximations for the population movements. If your sample is a true representative. Now, if there are good approximations, I can equate them and solve the equation. So very simple. So let us consider this example, which is about a sample from normal mu sigma square. Both parameters are unknown, mu and sigma. Find the method of movement estimators of theta. Is it based on a minimal sufficient statistic? So that is what I'll say. So if I have to do this example, let me just write down something over here. Let me call this as example 1. So I need to calculate, there are two parameters. So let us see whether first two movements, population movements, depend on mu or not. So what is my mu1 prime? So theta is mu sigma. Mu1 prime theta is expected value of x1, which is mu. I calculate the second movement, which is expected value of x1 square. Expected value of x1 square, you know, is same as variance of x1, which is sigma square plus mu square. What is m1 prime? The sample mean, right? The first sample movement. What is the second sample movement? Which is 1 upon n. Semi-semi is equal to 1 to n xi squared. So method of movement estimator is mu tilde and sigma tilde square. And how do you get it? You put mu tilde, the first, as x bar, and second movement is mu tilde square plus sigma tilde square as 1 upon n, summation I is equal to 1 to n xi square. Only this means. Second sample movement is 1 upon n summation xi square. So from here you get sigma tilde square as 1 upon n. So if I solve these two equations, I get mu hat tilde is x bar and sigma tilde square is 1 upon n summation xi square minus x bar square, which is basically 1 upon n summation xi minus x bar whole square, which is Sn square. So mu tilde sigma square tilde is x bar and Sn square. Sn square is the one which is based on n minus 1. Now, if you have to find the method of movement estimator of, let me call this as tau theta, which is mu tilde plus sigma tilde, would be what? Mu hat is x bar, sigma tilde is Sn, so x bar plus Sn. So very simple example, you might have done it many times at your bachelor's level. Similarly, you can do the problem number 2. You have a sample from binomial MP with M and P. So here, note that your method of movement estimator depends on a minimal sufficient statistic, x bar and Sn square. In general, it may not depend on the minimal sufficient statistic. For example, if you consider x1, x2, xn as IID uniform 0 theta, what is the first movement? Expected value of x1, which is nothing but theta by 2. So what is the method of movement estimator? Theta tilde by 2 is equal to first sample movement, which is x bar. And theta tilde is 2 times x bar. What is a minimal sufficient statistic in uniform 0 theta? It is xn, maximum of x1, x2, xn. And 2x bar, maximum xn is not a function of 2x bar. So 2x bar cannot be even sufficient. Forget about minimal sufficient. It's not sufficient. So that's a one disadvantage of method of movement estimation, that the estimator which you obtain may not be functions of sufficient statistic. And as we will see later, that if you are given any estimator which is not a function of a sufficient statistic, you can improve upon that by choosing an estimator which is a function of a sufficient statistic. So what it means in nutshell is that in the uniform 0 theta, you can find a better estimator than 2 times x bar. And the reason is because your estimator does not depend on the minimal sufficient statistic over here. So in general, your method of movement estimator may not depend on the sufficient statistic. Now then, this is a binomial MP example. Your M is, M and P both are unknown. Find the method of movement estimator of theta. Is it based on a minimal sufficient statistic? So first of all, can anyone tell what would be the minimal sufficient statistic when both are unknown? So F MPX would be product I is equal to 1 to n, M choose xi, theta to power p to power xi, 1 minus p to power 1 minus xi. Indicator that xi belongs to 0, 1, up to n. So you can see that there is no way you can revise this. What you can do at the best is product I is equal to 1 to. So this, each of them is factorial m. So that becomes factorial m to power n. Product of factorial xi's and product I is equal to 1 to n. Product m minus xi, p to power summation xi, 1 minus p to power mn minus summation xi, and then product of this indicator. So what is the minimal sufficient statistic? Can anyone tell in this case? So in fact, that would be complete sufficient.
So the random sample itself.
Yeah. Yeah. No, the whole sample may not be, because at factorial xi you are able to, at least you have been able to do this, right? Product I is equal to 1 to n. This all can, denominator can be written as product I is equal to 1 to n xi, factorial xi into m minus xi. So this and summation xi is coming. So this and summation xi, you can use the exponential family result, because this you can write down in exponential family thing. So your summation xi and product I is equal to 1 to n of factorial xi and m minus xi is minimal sufficient. In fact, it is complete sufficient. So it would be minimal sufficient. And if you have to get the method of movement estimator, what you have to do is, what is a mu1 prime theta? The first movement, sorry, not this example. This example, binomial example. What is the first movement? It is m times p. What is the second one? MP into 1 minus P. So what our method of movement says? M tilde P tilde is same as X bar, and M tilde P tilde into 1 minus P tilde would be nothing but 1 upon, sorry, second movement I have to look at. Right? Second movement, these are variance. Second movement is not this quantity. Second movement is expected value of X square, which is variance of X1, which is MP into 1 minus P. So we can put tilde because you're offering plus expected value of X1 whole square. So M tilde square, P tilde square is equal to 1 upon N summation Xi square. Now note that you can solve this in terms of M tilde and P tilde. That will turn out to be a function of 1 upon summation Xi square. But 1 upon summation Xi square is not appearing over here. So it will be only a function of your estimators M tilde and P tilde. You can obtain by simultaneously solving these two equations. They depend on X bar and 1 upon N summation Xi square. Whereas your minimal sufficient statistic was this. This is not even sufficient. If it was sufficient, you'd be in a position to obtain this from this, but that is not there. So this is another example where you obtain that your method of movement estimator is not a function of sufficient statistic. Now let us consider another popular method of estimation, which is called the method of maximum likelihood. So first I define the likelihood function for this. For a given observed sample point X, define Lx theta as product I is equal to 1 to N F theta X psi as a function of theta after you have observed the sample. So for a given observed sample X, I can define the likelihood function at the point theta for that observed sample. So likelihood function is defined for a fixed observed sample. Now note that these F theta Xi's are kind of a probabilities. So this together in a certain sense represents, if it is a discrete case, what is the probability that X1 is equal to X1, Xn is equal to Xn. So this in a certain sense represents probability of observing this sample from the population which is characterized by this theta, or from a population having probability function P theta. So this is a probability of observing the given sample when theta is the true state of nature. That means theta is the true parameter. That means what it happens. You already observe the sample, then you look at among all the populations, which population is most likely to give this as an observed sample. So that way, it makes sense to talk about maximization of this likelihood function with respect to theta. Because then the corresponding population would be most likely, because you're maximizing, so this is a probability that would be most likely to yield this sample. Or in other words, the sample would be most likely to have come from the density F theta X. So the probability that the observed sample point X came from a population represented by PDF, PMF, F theta X, that can be treated as Lx theta. Now you already observed the sample, so then you would like to see this sample was most likely to come from which population. So that way maximizing Lx theta makes sense. So that is what it says. It makes sense to find theta hat that maximizes Lx theta for a given sample point, as then the corresponding population represented by PDF or PMF is most likely to have yielded the observed sample. So you try to look at which population is most likely to give the sample which you have observed. And that is nothing but the maximum likelihood estimator. So that way you see the maximum likelihood estimator also has a lot of intuitive appeal. And unlike the method of movement estimator, the likelihood function will always, the maximum likelihood estimator will always be a function of sufficient statistic. Why? Because your likelihood function is nothing but a PDF. So by factorization theorem, you can always factorize your PDF so that it has a sufficient statistic factor. And you are maximizing that. So that means your data is coming through only sufficient statistic T, so your estimator would depend on sufficient statistic. So now I give a definition of a maximum likelihood estimation. This is all you have done at your bachelor's level, but again, I'm just reviewing it. So for a given sample point X, the function Lx theta as a function of theta is called the likelihood function. So likelihood function is nothing but a PDF considered as a function of theta for a given sample observation. For each X belonging to X, let theta hat be such that which maximizes the likelihood function. So Lx theta hat is supremum over theta belonging to theta of Lx theta. Or in other words, theta hat is the point at which the likelihood function is maximized. Then a maximum likelihood estimator of the parameter theta based on random sample X is theta hat X. Or in other words, the maximum likelihood estimator is nothing but one which maximizes the likelihood function Lx theta. Now note that when I take the supremum and this theta is an open set, there is a possibility that your supremum may lie in the boundary, because that is well known, right? When you are looking at the supremum of a function, supremum may lie on the boundary. So one thing you have to note over here is the range of MLE theta hat X coincides with the range of theta with boundaries of theta included. So for example, in the binomial 1 theta case, your MLE may take value theta, may take value 0. For example, in this case, MLE is X bar, binomial 1 theta. And X bar can be 0, right? Because each observation is 0, then X bar can be 0. So although here theta may be between 0 to 1, but your maximum likelihood estimator will take value in 0 to 1, but it can take value in the boundaries also. That is because of this supremum, because supremum may be attained in the boundaries. So MLE of the parameter or the corresponding PF for which the observed sample is most likely, so that we have already seen. In general, MLE possesses good optimum properties and hence a good point estimator. So these maximum likelihood estimator are the most popular estimators because they have very good optimal properties, as we will see in the later course, that they have very nice properties. Yeah. However, finding MLE may be sometimes cumbersome. So finding MLE requires maximization of likelihood function, which is sometimes difficult and may require numerical optimization techniques. So it may not be possible to get a closed form expressions for your MLE, and you may have to get the MLE in through numerical optimization. So one such example could be the gamma. So if x1, x2, xn is a random sample from gamma alpha theta, both are unknown, where alpha theta belongs to 0 infinity plus 0 infinity. This whole thing. I'll give this as an exercise problem. You would see that here you cannot get a closed form expression for the ML. And one has to resort to numerical techniques to evaluate these estimators. One criticism of MLE is that it is sometimes sensitive to data. A slightly different data may produce vastly different MLE. Right? For example, especially when there are outliers in the data, then it is very sensitive to outliers. So if one outlier comes into the data, like sample mean in the binomial case, then it can change the value very drastically. Now, since Lx theta depends on sufficient, in fact, minimal sufficient statistic, the MLE is a function of a minimal sufficient statistic, because your likelihood function is what? It product I is equal to 1 to n f theta xi. And you know, if T is minimal sufficient statistic, by factorization theorem, this can be written as psi theta Tx into Hx, if T is minimal sufficient. So your likelihood function depends on theta through Tx. And you'll be maximizing this. Hx is a constant because here sample is fixed. So Hx is 6 because you are maximizing with respect to theta. So maximizing this is same as maximizing this. So that means any maximizer is going to depend on observation only through Tx. So your maximum likelihood estimator is always a function of a minimal sufficient statistic. A very nice property, which was not the case for the method of movement estimators. Now let us look at how do you find MLE. Suppose that for given x in the sample space, Lx theta is a differentiable function of theta. Then you know that MLE, if you have a differential function of a theta, then you know that the optimal or maximum or minimum of a function would be either at the boundary or at an interior point. If it is an interior point, then the derivative there has to be 0. Then the MLE theta hat x is either on the boundary of theta or at a point where derivative is 0 with respect to each theta. So the contenders, if your likelihood function is a differentiable function of a theta, then contenders are the boundary points or the points where derivative is 0. Note that the points where one holds may be a local or global maxima or a saddle point. So solution of 1 should be checked for global maxima as well. Now note that sometimes maximizing Lx theta is same as maximizing log of Lx theta, because log is an increasing function. So whether you maximize Lx theta or log of Lx theta, they are one and equivalent thing. And log of Lx theta I denote by small Lx theta. So sometimes it may be more convenient to maximize log of the likelihood function, which I am denoting by Lx theta. So let us consider this example. Let x1, x2, xn be a random sample from a PDF, DMF f theta, where theta is unknown. In each of the following cases, find the MLE of theta. Now this example, normal theta 1, you might have done many times at your bachelor's level. Now, this point, you might not have possibly, because here now your parameter space is restrictive, which is theta is between 0 to infinity. So what does that mean? That means I have to look at a supremum over this. And I know that the maximum would be attained only at the interior point or at the boundary. So what it happens? So when I look at this, your likelihood function, log likelihood, in fact, I can look at. What is the log likelihood? Variance is 1, so 1 upon root 2 pi to power n would become constant. So that I involve in this. Minus summation xi square by 1 also become, I can absorb in this constant, which is a function of x. Then e to power minus twice theta summation xi. But you are looking at, so e to power n x bar theta. and then e power minus n theta square by 2 n theta square by 2. So theta square by 2. N theta square. Okay. The only thing is now my theta is given to be greater than or equal to 0. So I look at the critical point in the interior, Lx theta by L theta, which is nx bar minus n theta. This would be 0 if theta hat is x bar. But your x bar may not be greater than or equal to 0. So this would be an interior only when x bar is greater than 0. And you can look at the double derivative. Turns out to be minus n, which is less than 0. So this would be MLE if x bar is greater than 0. If x bar is less than 0, then your derivative does not vanish anywhere. And maxima exists because your likelihood function would be bounded. In fact, your density is bounded because of e to power minus 1 by 2 theta square. So maxima would exist. So that means the maxima would be on the boundary and boundary is 0. So your theta hat MLE in this case would be x bar if x bar is positive, and 0 if x bar is less than or equal to 0. So if your parameter space is 0 to infinity, then this is. Now you can find this in alternate way. You can look at the behavior of this function. Note that Lx theta is increasing if and only if theta is less than x bar, and decreasing otherwise. It will be decreasing if theta is greater than x bar. So your likelihood function turns out to be like this. If I consider whole theta, here it is the maximum. This is Lx theta. But I have to restrict my maximizing thing to 0 to infinity. So note that if 0 was over here, that means x bar was bigger than 0, then maximum, my theta would be on right of this, and maximum would be attained at x bar, theta is equal to 0. Now, if my 0 was over here, then my parameter space is on the right of it. So this is not included. And then Lx theta, because it is decreasing over here, would be maximum when theta is equal to 0. And that matches exactly with this. So all these examples, you can take x1 is binomial m theta, m is known. This you have done at your bachelor's level. X1 is binomial m p naught, where p naught is unknown. And m is, both are unknown, right? Where p naught is known, you can look at here, and m belonging to n is unknown. So try to do these. These are one parameter examples. These you have done many times at your bachelor's level. So here I gave you one example where the parameter space may be restricted, and you have to use the basic tools of your calculus to get the maximum likelihood estimator. One situation where both are, where you have more than one parameters. Now let's talk about invariance of MLE. So what we have done so far is you can get the MLE of the parameters associated with the PDF. But sometimes I may be interested in some function of a parameter associated with the PDF. How do you do that? So can I say that if theta hat is MLE of theta, then tau theta hat would be MLE of tau theta? That is what our intuition suggests. And that has a very strong basis, which will cover under invariance of MLE. So suppose that one is interested in estimating a function of the parameter which was involved in the PDF for some function type. So I now give first the definition of an induced likelihood function, because this would induce a likelihood function in the sense that you have a parameter space theta over here. This is a range of tau theta. So there is a tau. So what may happen is more than 1 point may go to the same. So this is a range of tau theta. There may be another one. They may go over here. There may be few points which may be 1 to 1. So here, what is the likelihood function induced by this? Now note that here, likelihood function for this and this is same because they are going to the same tau theta. So what I try to do is I try to look at what is the maximum of these two, and I define that to be the induced likelihood function at point eta. So what is the induced likelihood function at the point eta? I look at the maximum of all the likelihood values of a likelihood whose pre-image is eta. So that is over here. So for a given sample observation X, the likelihood function induced by eta, which is tau theta, is defined by Lx star eta. I look at maximum over all those likelihoods at these only points which are going to eta. So supremum over all those theta for which the image is eta. That is how define I Lx star eta. Now eta belongs to the range of tau theta. So eta belongs to theta star, which is collection of all those tau theta, such that theta belongs to theta. So this is the range of tau theta. So I look at supremum of this. So through this, I can get a likelihood function induced by tau theta. Then I look at the value and at eta hat that maximizes Lx star eta, and that will be called the MLE of tau theta. That's a very intuitive way of defining the MLE. The one, you know that when I'm considering the eta, I've considered the supremum over this. Now, if I keep on varying over etas, I can get supremum over all of these. So this suggests that if I look at the supremum over eta of all those Lr star etas, I will get the supremum of the original likelihood, because that is how it is defined. For this eta, I look at the supremum of these 2 points. For this eta, I will look at supremum of this. For this eta, I will look at supremum of this. So essentially what you are doing is, as you are varying eta, you are considering supremum of whole Lx theta. And that is what this note says. Note that supremum over Lx star eta as eta varies over theta star is same as supremum of Lx theta as theta varies over whole theta. That is clear from this figure. Otherwise also, it is like you find a maximum. First, what you do is you partition your space into smaller sets. You look at the maximum within each of these smaller sets, and then you look at the overall maximum. So this is a supremum. This is a supremum over smaller sets. Smaller sets means which are going to eta. And then you vary eta. That gives you supremum over the whole set. So now I prove the invariance properties of MLEs. It says if theta hat is the MLE of theta, then tau theta hat would be MLE of tau theta through this definition of an induced likelihood function. So I fix the sample point X. Let eta hat be the induced. Let eta hat be the point which maximizes Lx star eta, induced likelihood function. We are required to show that Lx star eta hat would be less than or equal to Lx tau theta hat. The tau theta hat would be the one which maximizes this. So we have Lx eta hat as supremum over eta of Lx star eta, which is supremum over eta of supremum over all those theta such that eta is equal to k theta. That is by definition. That is how you are looking at the definition of an induced likelihood function. And what is this? This is same as supremum over whole theta, which is same as Lx theta hat. So if eta hat maximizes Lx star eta, so that means if the induced MLE exists, then I know that the value at eta hat of the induced likelihood function would be same as the value of the original likelihood function at the point theta hat. Now I try to look at what is Lx theta hat. Lx theta hat would be less than or equal to supremum of all those tau theta over all theta such that tau theta is equal to tau theta hat. Why? Because theta hat always, because tau theta hat is always same as tau theta hat. So when I am looking at the set of all those thetas as that tau theta is same as tau theta hat, clearly theta hat satisfies this because tau theta hat is same as tau theta hat. And you know that supremum over a smaller set is smaller. So since theta hat is a one particular element of this set, supremum over a singleton is singleton only. So Lx theta hat is supremum over just singleton theta hat would be less than or equal to supremum over a larger set where theta hat belongs to. This is a larger set in which theta hat belongs to. So this would be less than or equal to supremum of this, which is basically likelihood function by definition of an induced likelihood function, that is an induced likelihood function at tau theta hats. But Lx theta hat is same as Lx star eta hat. So what you get is, in fact, this is same as Lx star eta hat by the previous step. So what you get is Lx star eta hat is less than or equal to, which is same as Lx theta hat is less than or equal to Lx tau theta hat, which says that, and since this maximizes the likelihood function, the other inequality is always true. So that means eta hat would be same as tau theta hat. So in fact, what it says is Lx star eta hat is same as Lx star tau theta hat. So either there is a unique maximizer, in that case eta hat would be same as tau theta hat. Otherwise, both would be maximizing the likelihood function point theta hat. So very nice property of MLE, which says that if theta hat is a MLE of theta, then tau theta hat would be MLE of tau theta. So you can just, for example, look at this example. Suppose x1, x2, xn be IID normal theta 1. Then x bar is the MLE of theta square, because in the normal theta 1 case, you know that x bar is MLE of theta. So theta hat MLE in this case is x bar. So what will the MLE of theta square will be? Let me call this as theta hat, which will be theta hat square MLE, right? Because it says, your result says that if theta is hat MLE is x bar, then theta hat MLE is square would be MLE of it. So which is x bar. Similarly, in the binomial n theta case, you know that x by n is an MLE. So what would be an MLE of theta into square root of theta into 1 minus theta? Square root of x by n into 1 minus x by n. Let me just introduce this small result from your calculus, which tells you how to find the maxima and a minima of a function, especially when your dimension is more than 1. So suppose D is a subset of Rn and f is a function from D to R. So that means f is a function defined on a subset of Rn and it is a real value. Suppose its partial derivative of f with respect to x1, x2, xn are continuous and have continuous partial derivatives. Let x0 be an interior point of D where derivative is 0, del f by xi is 0. So that means at x0 is a critical point of f, where derivative is 0. I consider the Hessian matrix, which is a matrix of second partial derivatives, because for finding the MLE, you will have to look at the Hessian matrix of the likelihood function or the likelihood function. Now, through the behavior of this Hessian matrix of the likelihood function, you can determine whether this critical point x0 was a local maxima or a local minimum. Now, if you know that if H is positive definite, or equivalently it has all positive eigenvalues, then x0 is a point of a local minimum. If H is negative definite, or equivalently has all eigenvalues negative, then x0 is a point of a local maximum. If H has both positive and negative roots, then x0 is a saddle point. Saddle point means from one side it would look like a minima. If you approach it from other direction, it would look like a maximum. So it would be neither a maxima nor a maximum minima. It would be a saddle point. So let us say what it happens in the two-dimensional case. If your matrix is A, B, B, C, symmetric matrix, because partial derivative Hessian matrix would always be a symmetric matrix. You know that this would be positive definite under what condition? If diagonal elements, one of the diagonal elements is positive and determinant is positive, that means AC minus B square is positive. A would be negative definite if A is less than 0 and AC minus B square is greater than 0. So this is the case of, and if AC minus B square is 0, then you get a saddle point. So let me stop over here for the time being. I have posted a new homework, which is basically on Massoud's theorem. It has problems dealing with only Massoud's theorem. So you may try to do that. Now, there is a possibility. So I would like to let you know that last couple of occasions, due to some technical glitches, I could not cover the portion which I was supposed to cover in that lecture. Especially in one of the lectures, there was a lot of issues and I could not cover anything. Similar thing happened in one of the earlier lectures. So I would like to have a compensatory lecture for this. So I'm proposing 12th of February, which is a Saturday. I can have from 11 to 12:15. So Saturday, I plan to take compensatory lecture. So be prepared for that. Now then, this Friday, I have to go out for this gate examination duty. So it may not be possible for me to take a lecture at 11. So I was wondering, Friday, can I take a lecture at 8, a tutorial? Does 8 suits everybody or not? Are you hearing me?
8 have a class.
8 you have a class. So what time on Friday? So Friday, that means I cannot have, because after that I have to. So let me see. Is there any time tomorrow I can have just this tutorial? But tomorrow you might not have tried those. So let us say Thursday. Thursday one I have, not Thursday. Let us say Wednesday, because Wednesday I'll have from 8 to 9. If another one I can have sometime in the evening, and then I skip the Friday one. So Wednesday, what time you are free? Can anyone let me know what time you're free on?
I guess after 12.
You know what time? Tell me. Any fixed time you tell. What about having at 4?
No problem.
4 is okay?
No, okay, sir.
Yeah. Okay. So I will have a tutorial Wednesday at 4. Friday we will not meet, and then I'll have a lecture on 12th, which is Saturday, a compensatory lecture. Okay, so that's all. And if you, for those who have any doubts, may stay back. Others may leave. They won't.
Sir, one question. Sir, okay, sir.
Tell me.
Yes, sir, towards the beginning of the notes, you mentioned some of the disadvantages of this MLE procedure. That if the data is changed, then the MLE may be very bad estimate.
It is very sensitive to outliers.
Yes, sir. But in real data, we know that there is a high chance of having outliers.
Right.
In real life data, sir. Then why do we use MLE at such a wide extent when this has such a disadvantage?
Oh, then you apply. Then what you do is then it becomes a problem of treatment of outliers. Then you have to study how to treat these outliers so that you can still use the MLE, but you have to modify MLE a little bit, right? So that becomes a separate topic, which will come under the treatment of outliers.
Okay, sir. Okay, sir. Okay, sir.
So there is a separate, because you see, outlier is always a problem, right? One way is the very easier way, is the lazy way, is you just ignore outlier, because the probability of obtaining outlier is very small, right? So
yes,
in real practice, the probability that you will be getting such an observation would be very rare. So why to bother about such a rare thing and give a estimate? So that is one very lazy way of doing things. But then there are better ways of dealing outliers, and one can deal with those outliers and can still use your ML.
Okay, sir. Okay, sir. Thank you, sir.
Yeah. So that is, you see, the way I said, no, for example, your sample mean has disadvantages, right? Especially if, in the presence of outlier, but still it is the most popular estimator, right? For the population, right? So it's not that any fixed estimator is foolproof. Everybody, each of the competitors would have some disadvantages, but if you compare the method of movement estimator and MLE, suddenly MLE looks much more appealing.
Yes, sir, because MME in any case will not depend on minimal sufficient statistic.
That is, method of movement estimator may not depend on a...
It may not depend on minimal sufficient statistic. Okay, sir.
We'll see that your estimators should depend on a minimal sufficient statistic, because such estimators are good estimators, as we'll see later in the course, right? Through Rob Blackman.
Right, sir. Right, sir. Okay, sir. Thank you.
Okay. Okay, so if let me know if there are other issues, otherwise we may just skip. Yeah.